to allow you to continue shifting left, bringing valuable insights earlier on in the design process. NX Immersive Explorer provides better visualization, provides better rendering, better virtual reality, better sustainable engineering, and ultimately, what matters most is better execution. It's designed in a way to give you complete control over how you operate within your design review, and it has handheld controllers to allow you to control everything within your virtual reality review. And both large and small scale models are supported. But I would say we might mention this at the end, but for more information, you're better to just take a look online. So the bulk of this talk today, of course, is about electronics and semiconductor and simulation. So, you know, the collaboration between our MCAD and our ECAD products is world class. And indeed, you know, we bought Mentor Graphics years ago, so you would expect it to be. And we'll take a little bit of time today to cover the basics of why that's so. But just before we do, we've got the time to mention an exciting new development announced in 20C12, which is PCB Exchange Connect. This is totally new. We've never had like an app-based tool for doing PCB design review before. So, PCB Exchange Connect, we're launching a design review tool, which is a cloud-based app that allows our users to access key engineering PCB parameters outside of CAD. You're probably familiar with NX PCB Exchange, or you may well be. It's within the NX suite of products, which is our ECAD and MCAD interface and can be used for design collaboration between designers in the domains of mechanical and electronics, for things like design review, for manufacturing, for preparation and simulation. Well, now with this NX PCB Exchange Connect, we offer a new innovation in the form of a dedicated app for PCB review and validation, designed to reduce process time. So Connect is a tool that will bring major benefits to designers and to analysts and other stakeholders in the design cycle. PCB Exchange Connect, it enables designers to use any MCAD, ECAD, or CE solution to collaborate on PCB design and perform key validation sooner during the design. And I do mean any tool. So any MCAD, any ECAD, or any CE solution, this is completely CAD agnostic. So with this product, there are no prerequisites in terms of the applications in use in your design environment. So PCB Exchange Connect can allow other designers and analysts to access key engineering PCB parameters outside of the traditional tools. You don't need to be a designer using existing NX with NX on your machine. You can simply access the data through PCB Exchange Connect, which you can do locally. And we've got a personalized web application development to meet your needs, with lots of different deployment options being supported. So NX PCB Exchange Connect, it enables project stakeholders to be involved in the design cycle as early as possible and have access to the current status of the PCB and the key CB parameters that they need, and see where they are within the process. It may be that there is impact from one discipline to another. Say, for example, you can imagine that a change to the PCB substrate affects the thermal performance of a board, which then might mean a rerun of simulation. So really, this is an application that's been designed to work to be used at different stages of the development cycle by multiple roles and stakeholders involved in the PCB. It's a broader set of stakeholders than traditionally we would have using NX, with the clear goal to decrease errors and promote collaboration amongst teams. So you may also have heard about NXX. What on earth is NXX? Well, we continue to innovate with NX, and we continue to strive to deliver new capabilities and applications and new approaches that help our customers run their businesses better, that hopefully help them improve their productivity and more often make use of the digital twin. And NXX is no different. It's in that line. NXX is building on the same product, the same user experience. It uses the same part files, the same data. It's basically using the same NX portfolio of information. Now, NXX removes much of the IT overhead because the software license, the configuration, and the updates are managed by us, by Siemens. But the software itself, the default condition you'll see is that we distribute and update the actual NX software onto our clients' desktops. So we're managing the configuration and updates, like think Office 365. You have all of the Office applications on your machines for all of your configurations, but your entitlements, you can do that too. We also offer an additional and optional stream service where we manage the entire NX instance and offer it as a streaming service. But many of our customers are simply looking for easier ways of managing the deployment and use of NX. They want the power of the product, but an NX which is easier to access and see that as engineering projects involve more domains, more disciplines, they get more complex. And complexity intensifies as different engineering domains work to co-design a single electronic system, many times without the tools and methodologies to ensure optimized development. Solutions that can't streamline cross-team collaboration nor share and manage data reduces between design and manufacturing. In this section, we'll look first at why multi-domain collaboration is essential for success in today's electronics market. Then we'll discuss how multi-domain collaboration, design collaboration, specifically electronics and mechanical co-design, can be applied to significantly improve the product development process. So, a multi-domain design collaboration in CAD is crucial for integrating the different design disciplines, improving efficiency and enhancing that design quality. It allows designers from various different domains, such as mechanical, electronic, and architectural, to work together seamlessly. By collaborating across domains, designers can simultaneously work on different aspects of a project, reducing design iterations and streamlining the process. Interdomain integration helps identify and resolve design conflicts early, saving time and effort. So, what are the challenges? Looking at this from the challenges point of view to the engineers and the designers. Well, synchronizing ECAD with MCAD. Different domains are typically or traditionally working with completely different tool sets. And the ECAD and the MCAD people have often completely different vocabulary. They're speaking a different language. Because of this, there are frequently workarounds to represent the other domain. So, for example, things like cutouts, keepouts, and height restrictions. What we tend to see in the industry today is that mechanical engineers are creating thousands of placement keepouts to represent the enclosure and other mechanical items, which is representing a 3D issue with a 2.5D object. This also makes it difficult for the electronic guys, the electronic designers, to understand where they can place their components, since there are so many draw items overlapping, given that you don't often work with a uniform square box for your enclosure. And other challenges, ECAD and MCAD projects are often completed by different organizations, by different file transfer, and it's often done rather late in the design cycle. And in terms of system verification, this is also continues to be a little bit problematic. Because each domain is working in a silo, there's limited awareness regarding system optimization. So if ECAD can't visualize or check against the enclosure or other boards in the system, there'll be extra iterations as they shoot in the dark for placement recommendations. And thermal simulation accuracy depends on understanding the mechanical characteristics, for example, enclosure contours and fans, as well as the electronic characteristics, which can be things like component power and the conductive properties of multi-layer interconnect. If this data isn't in one place, the simulation results are obviously less useful. The same can be said for EMI analysis. And all of this results in frequent respins due to problems being found in physical prototype integration. The goal of optimization, for example, for size or system performance, is simply untenable if basic alignment can't be achieved. Okay, so, the advanced technology associated with some of today's best-in-class tools, they address the organizational complexity by enabling seamless multi-domain collaboration during electronic systems design. And best-in-class tools that enable seamless multi-domain collaboration provide for things like a common electronic and mechanical parts library with a single item representation of the part footprint, symbol, and attributes, including both 2D and 3D part representations. They provide for multi-domain collaboration, adaptable to a company's workflow in either a synchronous or asynchronous use model that allows engineers to work in their native environments, and an integrated product-level BOM that contains all of the electronic and mechanical part information. Okay. Looking at, I'll go a little bit quicker through this, looking at the history of different data formats in the past, DXF and STEP were good at the time, but they do not necessarily contain all of the information, which would be all of the data which would be needed for true ECAD-MCAD collaboration, where IDF was certainly an improvement. It was released in 1992, and it was the first data exchange that was truly focused on exchanging all of the data that would be required, that is required for collaboration between ECAD and MCAD domains. While the IDF format, it does provide for bidirectional. It's an exchange of the entire data set each time during each collaboration cycle, which is not necessarily what you need or want. There's no ability to communicate incremental changes. And furthermore, there's no way to track the changes that are being performed over time. Where the state of the art for Siemens tools between, say, the likes of ephpTecsup and NX is IDX, or the interdomain design exchange, which was first introduced back in 2010. But like IDF, IDX is focused on exchanging all of the data that is required for collaboration between the electronic and mechanical domains. Or one of its benefits is that it provides true bidirectional collaboration along with traceability. And indeed, yes, IDX is it's an Excel format, messaging format that that is based on the ProStep ECAD design and MCAD design, open schema for the incremental exchange of information between ECAD and MCAD. And with this format, designers are able to synchronize their data more efficiently and collaborate more effectively on critical design items between domains, thereby ensuring that the design intent is properly maintained and implemented. And a principal benefit of IDX is that it provides this bidirectional collaboration along with traceability. And it also, with having an extensible data model, its flexibility allows improvements to be made to the format without impacting existing collaboration, without consequences in terms of backwards capability. IDX collaboration is a workflow where incremental design changes are communicated as transactions, which can be previewed, accepted, or rejected. They allow the PCB design or baseline to advance jointly between the teams in a controlled way. And we'll take you through an animation of that shortly. So yeah, and just as a little bit of a by-the-by, in an online poll that we ran recently, we compared companies, we asked companies what they were doing. We compared their different ways of exchanging ECAD, MCAD data. And given the challenges of exchanging data, many companies don't actually exchange data between domains at all. Or if they do, others use email or other general office tools. Some companies use IDF, developed in 1992, but surprisingly indeed, the take-up of IDX is astonishingly low. So there's a lot of improvement to be had in the market in general. So if we take a step through this, a typical ECAD MCAD workflow, but enabled by using Siemens applications, the collaboration between ephpTecsup and NX has 4 collaboration types enabled by our enhanced implementation of IDX. We layer some additional functionality on top of what the IDX standard by itself gives you. There is such a thing as the baseline proposal. This establishes the initial data set from either domain, from either ECAD or MCAD, and it creates unique IDs for all the current objects. Then there is a proposal which sends only the added, the modified, or deleted data made since the baseline was applied. There can be a response, which is a collaboration file back that replies to the other domain as design objects are accepted or rejected. And finally, there is the external type in the workflow. It's a one-directional data transfer from ephpTecsup, the ECAD tool, to NX, and that is not tracked in the history. In the initial state here, the MCAD engineer defines enclosure and a board outline to fit and critical component placements. Constraints are defined to check for in NX. The initial dataset is sent to Expedition to establish the baseline ECAD database, including board outline and critical components. The layout designer works to finish the placement within the placement constraints defined. Yeah, there's a little bit of latency there, isn't there? Okay, I'll click earlier. If the placement doesn't work, so for example, if parts are too close for manufacturability to be manufactured, or if part placement won't allow critical signal connectivity, then a proposal is sent to NX. And this proposal can include multiple requests for consideration. It's not just one at a time. The mechanical engineer considers the proposals and accepts or rejects them on a proposal by proposal basis, or proposes alternatives. And this proposal and response loop can occur many times. It can happen many times. While the placement iterations are taking place, the layout designer is busy. He starts with routing, focused on the already approved parts. And at some point, the layout designer finishes with routing and plane definition. And finally, the final external data, which is on this occasion is not intended for collaboration, is sent to NX. And this includes copper data that can be used for visualization as well as for analysis. Okay, to summarize on the core elements of our integration, the Siemens tools let you visualize in 3D in either NX or Expedition. They let you propose changes at any time from either domain. They use checkers in either environment to verify changes before approving, and they give traceability of decisions. Okay. All right. Just to summarize the value of effective collaboration to ECAD, MCAD disciplines. To help reduce time to market, consistent iterative communication helps design teams synchronize and avoid late rework in the process. More robust designs can also be created, and reduced respins allow the team to focus on optimizing the product through collaboration on what-if scenarios. And integration with analysis tools extends the ability to make trade-offs using the digital twin long before the first prototype. The net result is higher quality, higher reliability, and better performance of the end product, all while achieving tighter form factor requirements. Okay, and now I'm going to hand over to John for an in-depth look at simulation.
Okay, thanks, Greg. Really interesting stuff. Fascinating to see the depth of integration that we have between MCAD and ECAD. Yeah, and what I'd like to do is take a look at the benefits of shifting left with simulation in the development process. So I guess the first question has to be, well, why shift left? Why use simulation earlier in product development? And the reason essentially is that a shift left approach integrates continuous validation into the development process, which accelerates cycle time, it increases reliability, and reduces risk and cost. So a lot of good business reasons for it. Performance becomes a focus for everyone working on the product, providing a common goal across the different design disciplines. And what we find is that this working towards a common performance goal really greatly encourages collaboration and with it innovation, which again increases product quality and sustainability. From a sustainability perspective, focusing on the 3 R's as they're called: reduce, reuse, and recycle, really keeps design for end of life as a priority. Products often have to work in a variety of environments, and that needs to be considered as part of this integrated design validation. So in practice, from the outset of the development, the team needs to answer questions around performance. So if we take thermal performance of the system as an example, the team will need to answer questions like, how are we going to get 300 watts out of a box that size? What is the cooling solution going to look like? How big will the heat sinks need to be? That's important because we might need to reserve board real estate for mounting those heat sinks. Would using heat pipes help us? Do we need to consider liquid cooling and so on? And all of these questions have to be answered through simulation and have to be answered really at the outset of development because they affect the very basic architecture of the system we're producing. So let's take a bit of a look at the simulation technology that we have built into NX. FlowEFD for NX, as it's called, is part of our SimCenter portfolio of simulation tools. And that portfolio covers quite a wide range of analysis disciplines. You can see here, how the analysis disciplines based in NX map onto that. And what we've done is taken NX and simply extend it to include simulation. So it's the familiar NX environment, but with an extra flow analysis menu, a toolbar, and a project tree for the simulation model settings. So FlowEFD for NX is mainly a fluids and thermal solution that uses computational fluid dynamics, or CFD for short. In recent years, its capabilities have been extended to include structural mechanics and electromagnetics, and the structural capability includes both vibration and thermally induced stress. FlowEFD for NX was first released in 2011, and as Greg said, the innovation never stops. Since then, we've had a really strong focus on electronics-related applications. That's been driven largely by customer interest. And the applications range from high-speed digital electronics to power electronics, from chip packages to systems, and all the way up to data center racks and even beyond that. The product has a vibrant development roadmap, I would say, with two releases a year. Many of the features are really quite detailed in nature, and I thought I wouldn't try to explain those. So what I've done is I'm just showing you here some of the larger, more easy to understand enhancements from the last two releases. Electronics is a very fast-paced industry, as we know. So speed to results is critical, and we often focus on increasing performance aspects of the software. And increased interest in electronics reliability has driven the extension into mechanical stress simulation, and that now includes nonlinear effects. And being part of the same product means the stress simulation can automatically use results from the thermal simulation, so we're never actually leaving the NX environment. And as the industry adapts to advanced packaging technologies, which are very much coming at the moment, and manufacturing challenges around those are increasing, we've addressed this by developing a convenient way to model the behavior of boards as they pass through reflow ovens. So I wanted to talk a little bit about the four pillars of simulation. These are the pillars that sort of guide what we do on the simulation side. So these are our four pillars which guide our SimCenter development roadmaps. Model the complexity is about really ensuring the realism of the simulations, increasing their fidelity. And of course, the products that are being modeled are themselves getting more complex. Explore the possibilities is really aligned with Shift Left. It aims to help engineers explore, the widest range of design options in early design when there's the most freedom to make decisions around changes. Go faster, I guess, is somewhat obvious. Time is money, so it's not just about simulation speed, but rather the time taken to get to a result. So that includes faster model setup, etc. And then stay integrated is about maintaining a continuous digital thread of information through design and simulation, supported by data management in the form of PLM. So related to model the complexity, let's have a look at a couple of challenges and how we address them, just to give you a flavor of the sort of things that FlowEFD for NX is being used for. So one of the challenges in electronics these days is that the different aspects of performance, such as timing, signal integrity, and power integrity, can no longer really be treated in isolation. And one area where we see this quite a lot is power integrity of power delivery systems. As the voltages drop and currents increase, voltage drops due to neck downs in power planes have become critical in some designs. The high currents, often involving hundreds of amps, heat the copper conductors, and as the copper gets hot, its electrical properties change, and that, of course, affects the voltage drops. So for electrical engineers to close the design, their power integrity calculations have to be coupled with thermal calculations. The thermal calculation takes into account the heat generated in the power delivery nets, as well as heat from other sources, such as the components, of course. And then temperatures are fed back, so the voltage drops can be recalculated using electrical properties for the copper based on the predicted temperatures. And this is done by connecting SimCenter FlowEFD for NX with Hyperlinks PI, which is a power integrity tool from our EDA division, to give a fully automated temperature-aware power integrity solution. And what we find is if you go around this loop just 2 or 3 times, you get self-consistent results. One of the leading causes of failure in electronics assemblies is low cycle fatigue. That occurs typically in the package interconnect, and that's solder balls in packages that have a ball grid array underneath, or BGAs for short. The recent development in 2.5D and 3D, high density advanced packaging and advanced solders has led to really a renewed focus in this area. FlowEFD for NX provides a seamless approach to predicting package and board level reliability with native package and board design data read in directly from Expedition, as we've seen in Greg's part of the presentation. This provides an environment where temperatures can be used directly for advanced finite element stress solver that accounts for the complex behavior of the materials used in electronics packaging. And the use of native geometry throughout this process means that the full power of parametric CAD can be used to modify the design to reduce the stress and strain and so improve reliability. A systematic and intelligent exploration of the design space can really gain tremendous value from the models that people have put effort into creating. Novel design approaches can be identified that way, and the best design optimized for performance and robustness. So again, let's have a look at a couple of examples related to this. An important aspect of simulation is being able to study the impact of various design parameters that arise from variations in components, raw materials, processing in it, etc. Electronics really have a very high level of reliability, or require a very high level of reliability, so that only a few parts per million are really allowed to fail to meet their design requirements in terms of acceptable performance. And companies that operate at high levels of process maturity, as it's called, account for these distributions during design to predict rates of product failure during development. To get an accurate measure of the number of parts that fail, to meet specification at such high levels of reliability requires a very large number of simulations. And to do this, surrogate models are used that are extremely fast to compute. And this can be done with SimCenter HEEDS, which is another product of ours. HEEDS is a design, analysis, and optimization software that also automates workflows between tools to allow multidisciplinary design space exploration. The optimization capabilities of HEEDS are also built into SimCenter FlowEFD for NX. Printed circuit boards are subject to various stresses over their lifetime. Investigating thermomechanical stress shock and vibration during design can greatly enhance a product's reliability in the field. SimCenter Flow EFD for NX uses native ECAD and MCAD data, as we've seen in Greg's part of the presentation, but without the need for simplification prior to the simulation. Our unique smart PCB technology provides a highly efficient and accurate modeling approach for the circuit card assembly, covering thermal, thermomechanical, shock and vibration behavior within the system. As development schedules are compressed, simulation turnaround times become a critical factor. Let's see how Flow EFD for NX allows you to embrace complexity and really stay within your expected time frame, increasing velocity right across the development process. So complexity has been noted as a growing challenge in the accurate simulation of electronics products, boards and systems. Our smart cells technology uses the intersection of an octree-based grid with the intersection of the geometry in order to create the computational mesh. The accuracy is controlled through the local mesh refinement on the unsimplified geometry. This technology really completely eliminates the need to simplify the geometry for simulation. And that's important because simplifying the geometry is an activity that doesn't add value to the final result, but it consumes a considerable amount of engineering time. It's a process that has to be repeated whenever the geometry is updated, again consuming engineering time. The realism of the simulation results is reduced, which reduces confidence in their interpretation and so adds risk to any subsequent design changes. SimCenter Flow EFD for NX avoids all of these problems. Another challenge when modeling electronic systems is that some of the geometry, such as cooling components, often not present in the CAD model. These are, commercial off-the-shelf components that are bought in, so they're not designed as part of the product. So often only a simple representation, such as a bounding box or a shell, may be included, for example, to just ensure that interference issues are avoided. So taking fans as an example, the flow rate versus pressure drop characteristics of these devices is needed for a thermal simulation. In some cases, the detailed fan geometry may be needed so that we can directly represent that as a spinning impeller within the model. And similar comments apply to heat pipes, heat sinks, gap pads, and other cooling components. And in some cases, even the enclosure itself is a commercial off-the-shelf component. And lack of this data really hampers simulation of performance in early design. So to overcome this, Flow EFD for NX provides a comprehensive list of what we call smart parts. Smart parts are intelligent modeling objects that are parameterized with specific instances from vendors available in a library. These models can be dragged and dropped into the model to accelerate early design tasks, such as fan selection, heatsink sizing, etc., which greatly speeds up simulation, particularly during early design. The last pillar is stay integrated. Increasing process and product complexity gives really more opportunities for misalignment between teams. So traceability is key to ensuring visibility and a continuous process that connects really all the relevant stakeholders, models, and data. And we refer to this as a digital thread. Simulation models and their results obviously form part of that digital thread. This is just one slide from a series of slides that the scope of which kind of extends beyond the scope of this webinar. And Greg has already covered very nicely the integration of electronics design and mechanical design. We have, as you've seen, analysis embedded into Siemens NX. Our analysis technology has a number of unique features that make embedding in NX not only possible, but a highly efficient way to shift simulation left in the development process. The user never leaves the familiar NX environment. There's no need to simplify or change the geometry for simulation. The process is guided by a wizard, making the model setup and simulation easy, with results displayed directly on the CAD geometry. The solution includes a parametric study capability, giving the ability to explore different design choices, and is supported by Sherpa, which is a sophisticated adaptive search capability to optimize design performance. I'd just like to show you a quick video to show FlowEFD for an X in action. I'll just quickly talk over that while it's playing. So what we have is the CAD model of the enclosure, and we're going to import the PCB from Expedition. We bring that in through EDA Bridge, which allows us to check the board data, add thermal models for components, etc. And then that assembly is transferred to NX as a smart PCB. In FlowEFD for an X, we can see the components and the powers attached to them. We go on to add the other boundary conditions, so those are the thermal loads. Then we apply other conditions such as fixing temperatures on the mounting brackets. We may know the temperature of the thing this is going to be mounted to, or the maximum temperature of the thing it's going to be mounted to, and the surrounding air, if you like, forms the rest of that. Then we build the mesh. That's done automatically just with a slider bar, and we can refine it locally with a slider bar. And then we solve the model. We can see the progress, and we can see the results stabilize. And then we can have a look at the results directly back on the model by viewing slices through it, looking at surface temperatures and component temperatures. And we can see the profile of the airflows, both inside the enclosure and outside of it, and then finally showing the casing temperature. Okay, so we just stop that and move on. I just wanted to share one example from a long-standing customer. This is from Seiko Epson, who've been making projectors for a number of years. Their challenges are, really around the brighter, more functional, smaller challenges. So issues associated with the higher light output. They wanted to also accelerate their product development cycles, as well as dealing with those challenges. And for each application, the products need to be, really compact, lightweight, portable, and most importantly, durable. But for them, the most important consideration in selecting a simulation tool was that all of the team members could use it, regardless of their level of ability. So the CAD integration was really key. I just have a couple of slides to summarize before handing back to Greg to close out the webinar. So we've kind of asked the question, as it were, how can we manage the complexity of the products? How do we develop increasingly complex products, reduce development time and cost, and really reduce time to market with a winning product? Or put another way, how can we turn complexity to a competitive advantage? And I think what we've shown you, or hopefully what we've shown you, is that the way to do that is to really focus on looking at performance early within the development workflow. So shifting left with simulation and doing that with analysis embedded into NX with our SimCenter FlowEFD technology. And with that, I'll hand back to Greg to close out the webinar.
Okay, thank you very much, John. That's very impressive. We are nearly out of time. We've kind of outrageously gone over our own time, but I think we've got time for a couple of slides here, just to round off. Returning, thinking for a second again about the digital enterprise at Siemens, we've helped many customers, hundreds of customers, along their journey to becoming a digital enterprise by combining the digital world with the real world with a comprehensive digital twin approach, enabling a continuous loop of optimization. I think the use of appropriate mechanical and design and simulation tools can also help you reach sustainability goals. For example, as we saw earlier, investigating the thermomechanical stress, shock and vibration during design, and then being able to mitigate their effects in the finished product can greatly enhance a product's reliability once it gets into the field, leading to more durable and sustainable devices. Furthermore, Flow EFD lets engineers simulate and analyze fluid flow, heat transfer, and other types of phenomenon within a design by accurately predicting and optimizing the thermal performance and stress response of electronic systems. Engineers can design more energy efficient products and processes. This leads to reduced energy consumption, lower greenhouse gas emissions, and a smaller ecological footprint. The seamless integration of Flow AFD with NX will help you develop more sustainable products more efficiently. And okay, alrighty. The combination of Siemens and NX and Flow EFD provides several benefits when used together. So the seamless integration point of view, the NX and Flow EFD are designed to work together seamlessly, allowing for efficient data transfer and collaboration between CAD and simulation environments. We have analysis embedded into Siemens NX, and our analysis technology enables embedding in NX not only possible, but also it's a highly effective way to shift simulation left in the development process. The user never has to leave the NX environment and doesn't need to simplify or change the geometry for simulation. This integration streamlines the workflow, eliminates data translation errors, and ensures accurate simulation results. So I think we've just about come to the end of this. We'd like to thank you for watching. If you've got any questions, there's still time to get some into the chat there. Or if you'd like to request more information about our solutions, please feel free to reach out to us and we'll get back to you. If you'd like to view more information right after this webinar, please use your camera to scan the QR codes and access some MCAD and simulation resources available behind these. You also will find the resource list off to the side and you'll be able to get immediate access to an electronic systems design trial by clicking on demo. And now, thank you, John. I'd like to hand back to Matt to see if there are any questions.
Excellent. Thank you so much, guys. That was incredible. Thank you for that great presentation. To the audience, we are almost at time. However, we feel we have time for one or two questions, so we're going to try to answer a couple. If you have any questions or comments for the team, now would be the time to send them in. We may not have time to answer them during today's session. However, if you do send in a question, it will be responded to over email after the webinar is over. Okay, let's try to get a couple questions in here. Okay, great. Here's a good one to start. Is NX free to educators? Guys?
Yes, it is. I'm kind of looking to Google this myself. The best approach to that is to search online for Student Edition. There are licenses available, controlled term licenses available both for students and for educators.
Excellent. Thank you for that. Okay, and interesting enough, this question actually came in multiple times in different ways, so we're going to go ahead and address this one as well. What is the best way for me to get started with simulation in NX?
Okay, I think that's probably for me. One of the things we provide literally online, you can find it by just searching, Flow AFD for NX trial. In Google is a free 1 month trial of the software where you can go in. It's a full install of the software, so you get to experience all of the features, but in a guided way. We provide tutorials for you to work through so that you can really learn all of what there is about the software.
Excellent, thank you for that, and thank you for that question to the multiple people that sent that in. Looks like we have time for one last question. Let's just see what we're going to choose here. Okay, this one looks great to close it out. Here's our last question from the audience. And again, to the audience, if we didn't address your question, we will reach out later. And if you have any last questions, please send them in now. You could type that info in the Q&A box and click submit, and we'll reach out to you later. But for now, this is our last question for today's session. Can you give me some examples of how simulation can help with sustainability?
Yeah, I think one of the things about electronic products is that there's a lot of cost and material, and so if you can use simulation to optimize, for example, a heatsink design, if you can make the weight of a heatsink a little bit less over the volume of the products that are produced, the resource savings are enormous, and the same comments apply also to trying to make sure that the cooling system itself doesn't consume more power than is necessary.
Excellent. Thank you for that. And thank you for that question. That was a great question. Okay, we are at time here, so we are going to wrap things up. So once again, Greg and John, thank you so much for the great presentation and also taking the time to answer a couple questions from our audience. And of course, we'd like to thank our audience members for being part of this webinar event. You will be receiving an email from us with a link to the on-demand version of this presentation, so you can come back and watch this again or share it with your colleagues. And lastly, please take a moment to complete a survey which will appear on your screen at the end of this live webinar. For on-demand viewers, you will find the survey located along the bottom of your attendee console in the survey widget. Again, thank you for taking the time to attend this webinar event. Take care, and we will talk with you soon.